So in the previous two problems, we could solve differential equations using the Laplace transform when the initial conditions were given at the point 0. So we needed to know y at 0, prime at 0, etc. Now, what if the initial conditions are given at a different base point that is not 0? So, for example, if we want to solve the initial value problem, w double prime minus 2w prime plus 5w equals negative 8 times e to the power pi minus t, where the initial conditions are given as w at pi equals 2 and w prime at pi equals 12. So now our initial conditions are not given at 0. So what we're going to do is we're going to transform the function w as follows. So it's basically a substitution. So we're going to use the substitution y of t equals w of t plus pi, or equivalently, you could also say that w of t is y of t minus pi. So what that does is, if you look at y at 0, you plug in 0 here, you get w of pi. And so you will be replacing this right here with y of 0 equals 2. And if you take the derivative of y, so y prime of t is then w prime of t plus pi. And by the chain rule, we have to multiply this by the derivative of t plus pi, which is just 1. So we see that y prime at 0 is w prime at pi. So this would translate then into y prime at 0 equals 12. So if we use that transformation, then we can replace our initial conditions at any point pi, or any point here, by initial conditions at 0. So now let's take a look at our differential equation. So I can rewrite my differential equation as w double prime, and now I'm going to shift all of this to t plus pi, right? And then minus 2w prime at t plus pi. And then plus 5w not at t, but at t plus pi. And then on the right-hand side, I get negative 8 e to the power pi minus t. I'm going to replace t again by t plus pi. And let's simplify that. So w double prime of t plus pi, that's going to be y double prime of t, and then minus 2 times y prime of t, and then plus 5 times y of t. And then on the right-hand side, pi minus pi, that's 0. And so I just have a negative t here. So this is minus 8e to the power negative t on the right-hand side. And we already saw that our initial conditions for this were y at 0 equals 2 and y prime at 0 equals 12. But this is exactly the initial value problem from example 1, the first video for section 7.5. So in that section, in that example, right, example 1, we found that y of t is equal to negative e to the power negative t plus 3 e to the power t cosine of 2t plus 4 e to the power t sine of 2t. So now when you have the solution for y, we're not quite done because we want a solution for w. So now we need to use the fact that w of t is y of t minus pi. So here we're going to write w of t is y of t minus pi. And so that's negative e to the power negative t minus pi, and then plus 3 times e to the power t minus pi. And then we have cosine of 2 times t minus pi. And then plus 4 times e to the power t minus pi times sine of 2 times t minus pi. Now that would be an acceptable answer, but we can actually simplify that a little bit. So Wt is actually minus e to the power pi minus t. And then here we have plus 3 times e to the power t minus pi. And then when you work this out, when you distribute the 2, you get cosine of 2t minus 2 pi. So, but because cosine is periodic with period 2 pi, that's like adding a full revolution to the circle to figure out the cosine. So we can actually ignore that. So because cosine is periodic with period 2 pi. And so the second part is 4e to the power t minus pi, and then sine of 2t. So the same argument here. So let me write that down, what I did there on the side. So cosine of 2t minus 2 pi. That is just cosine of 2t, and sine of 2t minus 2 pi simplifies to just sine of 2t. So that's what I used here and here. And then that is our final answer. Now, the Laplace transform can also be used to solve certain linear differential equations with variable coefficients if we use the following property of the Laplace transform. If f of t is piecewise continuous on the left closed interval from 0 to infinity and of exponential order alpha, then the limit as s goes to infinity of the Laplace transform of f has to tend to 0. Now, in particular, of interest for us is that if y is differentiable, then it is piecewise continuous. And so then we have that the limit as s goes to infinity of the Laplace transform of y, which we typically denote by capital Y, then that limit has to equal 0. So in the next video, I'll show you how we can use this property to solve a differential equation with a variable coefficient.